So welcome to this session where we look at how we can analyze sequential circuits. The sequential circuits we've discussed thus far can perform very simple functions such as shifting or counting, but we need to be able to perform more complex things. The counters we designed to go through fixed sequence of states and have no inputs other than a clock that causes them to change state. We will now consider sequential circuits that have additional inputs. In general, the sequence of outputs and the sequence of the flip-flop states for such circuits will depend on the input sequence we've applied. Given a sequential circuit and input sequence, we can analyze the circuit to determine the flip-flop state sequence and the output sequence by tracing zeros and ones signals through the circuit. Now, you should, at the end of this session, be able to analyze a sequential circuit by tracing the signals. Given a sequential circuit, write the next state equations. Given a state table, construct the corresponding state graphs. Explain the difference between a Mealy machine and a Moore machine. And draw a general model for a clocked Mealy or Moore sequential circuit. 4 key things that you should know: how to design a sequential parity checker, analysis by signal tracing, state tables and graphs, and then general models for sequential circuits. The recommended test is chapter 13 of Fundamentals of Logic Design, which I urge you to read. Although signal tracing may be adequate for small circuits, for larger circuits it is better to construct a state graph or state table which represents the behavior of the circuit. Then we can determine the output and state sequences from the state table. Such graphs and tables are also useful for the design of sequential circuits. The first type we want to look at is a parity checker. Right. So we talk about even parity, odd parity. So you have 7 data bits and then you add a parity bit, right, to give you an 8-bit word. The parity bit will count the number of zeros or will count the number of ones in the signal, and then if it's an odd parity, it will add a 1 to the parity bit if the number of ones in the data is even. So in this case, they are all zeros, and therefore we add a 1 there. In this case, there's a 1, so it means it's a 0, and so on. So when binary data is transmitted or stored, an extra bit is normally added for error detection purposes. For example, if data is transmitted in groups of 7 bits, an 8th bit will be included as a parity bit. Alternatively, the parity bit could be used such that the total number of ones in the blocks could be even or odd. So it depends. So you can have a parity, odd parity or even parity. As a simple example of a sequential circuit which has 1 input in addition to the clock, we will design a parity checker for what? Serial data. Serial means that the data enters the circuit sequentially, that is 1 bit after the other. The circuit has a form shown here. Yeah? It has a form shown there, and we are interested in the output Z. So Z should be 1 if the total number of inputs received is odd. That is, the output should be 1 if the input parity is odd. Thus, if the data which originally had odd parity is transmitted to the circuit, a final output of Z equals to 0 indicates an error in transmission has occurred. So this is what you want to do. So you can start by constructing the state graph. Yeah? A state graph is something that will pictorially help us to understand, picture the thing. So a sequential circuit such as this must remember whether the total number of ones received is even or odd. Therefore, you only need 2 states because you want to remember whether it's even or odd. Yeah? So state 0, yeah, Z will be equal to 0. State 1 Z equals to 1. So this state 0 and state 1, which will correspond to an even number of bits and an odd number of bits. So basically, this is what you have. This is a state graph. So if you are in state 0 and the input is 0, then you remain in that 0, in that state, because the total number of this is still 0, right? Now, if you're in this state and then you receive a 1, then you move to the next state because the total number of 1s now has changed. And then if you're in that state and you receive a 0, right, then you remain in that state because the total number of 1s will be unchanged. Now, if you're in this state, state 1, and you receive a 1, then you have to go back into state 0. So this is how this thing would look like basically. Right. We can then draw a state table for this. So your present state, S0 or S1. Then your next state, yeah, when you next state, if you receive X or equals to 0, or if you receive X equals to 1. So if you receive X equal to 0, that is from the state graph, yeah, then you remain in that state. But if X equal to 1, you move to the next state, and the output then becomes 0. Yeah, and then in this state, you know, if you get X equal to 0, you get an input, you move to state 1, you remain in that state 1. If the output equals, input equals to X equals to 1, then you move to state 0 again. So this is a state the state table, which you can derive quite easily from the state graph, from this state graph. So from this state graph there, you derive the state table. And once you got that, you can then quote this information of the various states, right? So you use, for example, 0 to represent state 1 and 1 to represent state 0. So then, knowing that you use the codes of zeros and ones to represent the movements from one state to the other. And you can then see that we can simply use a flip-flop, you know, to represent this whole state position. So that diagram is what this is what you get at the end of the day. So here I want to analyze clock circuits, you know, from a given input sequence by signal tracing of zeros and ones, right? Now, there is a basic procedure you follow. You need to construct a timing chart which shows a relationship between the input signals and the clock and the flip-flops. You know, you assume an initial state of the flip-flops. You know, all flip-flops are reset to 0 unless otherwise specified. For the first input in the given sequence, you determine the circuit outputs. You determine the new set of flip-flop states after the next active clock edge. You determine the outputs that will correspond to the new states, and then you simply repeat steps 2, 3, and 4 for each given input. So you need to use an edge-triggered flip-flop. The flip-flops will be sufficiently stable before and after the clocks. You know, the changes that occur in response to the active clock edge, you know, the circuit output may change at the time the flip-flop changes. So we use an edge-triggered flip-flop that change the state after the active edge or the leading or rising falling edge. The circuit output may also change at the time the flip-flop changes state or the time the input changes, depending on the time of circuit, you know. There are two types of clock sequential circuits that you come across, you know, or will consider. This is the Moore and the Mealy types, you know. The one in which the output depends only on the present state. Yeah, and those in which the output depends on both the present state of the flip-flops and the value of the circuit inputs. Right. If the output of a sequential circuit is a function of the present state only, And then we call that a Moore machine, right? So Moore machines are those in which the output of the sequential circuit is a function of only the present state. So the present state determines the output. So in this circuit, for example, the initial state A equals to B equals to 0, and all the state changes occur after the what? The rising edge of the clock, as is seen in the timing diagram. After the rising, so the changes will occur after the rising edge. The input is synchronized with the clock so that it assumes the next value after each rising edge. And because Z is a function only of the present state, the output will only change when the state changes. So the output will only change when the state changes because there's no other input to the Z except from the present two states. So if you see, you can see that the Z output, it takes its inputs from these two states only and nowhere else. The Mealy machine, on the other hand, is one in which the output is a function of both the present state and the inputs. So not only does the present state affect the output, but then the inputs also have an impact. So we have been looking at how to analyze clock sequential circuits by signal tracing. Although this is satisfactory for small circuits and short input sequences, when the circuit gets a bit complex, then this becomes quite difficult to do. So it's useful to look at state tables and state graphs, which we touched on briefly when we talked about the parity checker. So the transition table and the state tables for a sequential circuit specify the next state and the output of the circuit in terms of state and input. A state in a transition table is specified by the flip-flop output values corresponding to the state. A state in a state table is specified symbolically. When analyzing a sequential circuit, the transition table is derived from the circuit. Given a transition table, a state table for the circuit is also derived by assigning symbols to it. So the following methods can be used to construct the transition table. You should determine the flip-flop input equations and the output equation from the circuit, and then also derive the state equations from each flip-flop from its input equations. You can use any of the following relations. If you're using a D flip-flop, then the next state equals to D. If you're using a DCE flip-flop, then the next state equals to D and CE, or a Q and a C not E. And for a T and an SR or a JK, the equations for the next states are shown. But we would concentrate only on the D state for the moment. You don't worry too much about this at the moment. So to do this, you need to plot the next state map for each flip-flop. You need to combine these maps to form a transition table. Such a transition table then gives the next state of the flip-flops as a function of their present state and the circuit input. So you need to plot the state map and then combine these maps to form a transition table. So, as an example of this procedure, let's see how to derive the transition table from the circuit shown. So you have this circuit, now you want the transition table. So the DA is X or exclusive or B. DB is X or A. And then Z will be the exclusive OR of A and B. So the next state equations, yeah, for the flip-flops are A will be X or X exclusive or B naught, and then for B it will be X or A. Now, let's look at the general models. Details of this you will find in your textbook, which you can study and then understand better, get a better understanding. Now, what are the general models for sequential circuits? Now, the general model for Mealy circuit using a clock D flip-flop is as shown. So we said the Mealy one depends only on the what? The outputs of the states or the present states, not on the input. So in other words, when you look at this, you see that you have a combinational circuit, right, with inputs x1 up to xm, and that's from the combinational circuit that feeds into a sequential circuit, and the sequential circuit are the memory elements. Now the outputs of this are taken back into the sequential circuit, but you don't see any connection from the inputs into the memory elements. All right, you don't see any input in the memory elements. So you can of course write the equations for the outputs, yeah, the Z outputs and the Q outputs as is shown on the right side here. Your task is to analyze the following sequential circuits using a state table and a timing chart, and then derive the next state and output equations. So for these circuits that we've shown here, can we write out the equations for A, the next state A, B, and the output Z? This brings us to the end of this session and also to the end of this course. There are a number of interesting topics that we've not had a chance to cover, but I would urge you to what? Read the textbook, and then you'll be able to see. So it's just an introduction. We just briefly touched on the various topics. Important details you find in the textbook, and your tutor would support you to better understand the topics that need to be covered. Thank you.